Good evening. Thank you everyone who is here listening to us today. We're very lucky to have Associate Professor Joseph Lizier to talk to us about complex system. So he's going to give us introduction to complex system, and please feel free to ask any questions that you would like in the Q&A. And at the end of this session, we'll be very happy to answer all your questions. So, Professor Lizier.
Fantastic. Thank you very much, Carlos, and good evening, everyone, whether you're watching live or maybe on a recording later on. Before I give you some background to me, I'd actually like to ask for some background for you if you're watching this live. I'm really interested to know what your background is, whether you're coming from a maths background, a physics background, computer science, engineering, biology, economics, or so on. If you're watching live and you're brave enough, I'd love it if you would put that in the Q&A for us. I'll give you a couple of minutes while I introduce myself, and then we'll check back in and see what replies we have there. And this is quite important because our Master of Complex Systems degree is very much about interdisciplinarity, looking at complex systems across all these types of domains and bringing together students from those different domains in the classroom to learn those different perspectives together. Anyway, we'll check back in on your background domains in a moment. Let me tell you about my background domain. My undergraduate degrees were in electrical engineering, specifically in communications engineering, as well as in science, in physics and computer science. After I graduated from those undergraduate degrees, I worked in industry for the better part of a decade. I was a research engineer at Telstra in the research labs, and also worked at a startup company in telecommunications for a while as well. After that, I got involved in more basic research in complex systems, and that led me to become an academic at the University of Sydney about 6 years ago now. And so there, I'm a member of our Faculty of Engineering, and I teach into our Master of Complex Systems degree. The courses that I teach are our Introduction to Complex Systems and another course called Self-Organisation and Information Theory, but we'll look at those later on in the evening. My research areas in complex systems are about looking at how complex systems process information. So looking at systems like the brain and asking how can we measure how the brain is processing information and making decisions using the tools of complex systems. This evening, what we're going to do in this masterclass is I'm going to give you an introduction to what the concept of complex systems means and what the relevant concepts we use to study and talk about complex systems are. I'm going to give you a presentation for the next around 30 or 40 minutes. There'll be some demonstrations included in that as well of some software tools that we use in teaching complex systems in our degree. And then we'll have some time at the end for some Q&A interaction as well to take any questions you have about the subject material or the degree itself. So at this point, let me check back in with Carlos and ask whether anyone's been brave enough to post what their background domains are in the Q&A.
Hi, Joseph. It seems our audience is a bit shy today.
The audience is shy. That's okay. That's all right. As I said before, in our complex systems degree, we have students from lots of background domains, from maths, from physics, from computer science, from engineering, from biology, from economics, and so on, because complex systems is relevant to all of these domains. We'll see that in some of the examples we look at in the next few slides. So we really welcome that. It is hard tailoring courses to people coming from so many different domains, but it's a strength as well. It's great to have people bringing all those different domains to the classroom and helping each other to learn about their own domains and learning together about the tools that we use across all of them. So let's start by asking, what are complex systems? When we do this in class, in our Introduction to Complex Systems degree, I usually ask the students, to give me their suggestions on what they think complex systems are and how they can be defined. We won't do that tonight. We're in more of a lecture mode at the moment. But if you're watching this on a recording, it might be a good idea to pause the video for a minute and think, how would you define complex systems? I presume you know something about them because that's led you to watch this presentation. But how would you define them? What we'll do live though is before I get to a definition, I'm going to talk about some examples. Often it's easier to start with examples to think about what we mean here before we get to a definition. Here are some classic complex systems that we look at in biology. We talk about the phenomena of schooling in fish, related to flocking in birds and so on. We talk about ants foraging and building trails, and we talk about synchronization in fireflies. Looking at each of these examples specifically, the schooling of fish is one of my favorite examples here. The schooling of fish forms some really amazing patterns where the fish basically move together as one in the school. And this can be basically in a straight line as we're seeing here. They can form tornadoes that we'll see in the next couple of slides. And they can also make really intricate turns, and we see large turning waves of the whole school to do things like avoid a predator or avoid an obstacle. What we see is that the fish closest to the predator will usually turn first. That will have a knock-on effect to the fish next to it, who has to turn to either avoid it or gets the signal that a predator is nearby. That will have a domino effect to the fish next to it again, and so on until we get this whole wave of a turn across the fish. And that embodies something known as the Trafalgar effect, named for the Battle of Trafalgar, when the English ships all turned in a similar formation like that. And it's really quite amazing. We get these kinds of emergent behaviors without any one fish being in control. There is no leader fish telling all the others to do that. It's a behavior that emerges out of the interactions of these many, many individual fish. Similarly, when ants forage to bring food from different food sources back to their nest, there's no ant that's in charge of that process. All the ants are acting effectively independently, and yet they are able to coordinate their activity to form these amazing trails between the food sources and the nest and to bring the food back. How do they do that? That's something we'll look at in a few slides' time. Looking at fireflies then, each individual firefly is able to flash. They are also able to coordinate their flashes such that if we were watching this in nature, we would see the whole collective flash at once and go silent, and a few seconds later flash again. Again, the question is, how do they organize themselves to be able to act in synchrony like that? There is no one firefly that's in charge. Again, this amazing behavior emerges out of their interactions. Still with biology, another of my favorite complex systems is the human brain. The human brain consists of billions of neurons, which are all really simple. All they do is receive small, discrete electrical impulses called spikes and release spikes to other neurons in the system as well. And yet, out of the interconnectivity of billions of these simple elements together, we get amazing behaviors of intelligence and consciousness. It's one of the holy grails of science to ask, how do we get emergence of consciousness out of such simple elements? We can look at complex systems of humans, not just inside the body, but outside the body as well. We can talk about social networks. We can talk about the network of your family, who's related to who. We can talk about the networks of your friends, and we can talk about social networks online, looking at how your friendships map in Facebook or Twitter or other social networks. In 2020, social networks have been really important because we've been looking at how epidemic diseases like COVID-19 spread in social networks, and looking at making interventions in those networks, such as lockdowns and having travel restrictions, to break those links and prevent the disease from spreading. So this sort of science is very important for understanding processes like that. We can look at engineered systems that we refer to as complex systems as well, like the internet, whose structure looks very similar to networks that we would see in the human brain or between genes in the human genome, and so on. We can look at traffic patterns, such as this enormous highway in China that starts to exhibit collective behavior like what we see in the fish. It's really important to understand complex systems, not just to understand how the world around us works in nature, but how to engineer human systems to take advantage of the important properties of complex systems and avoid some of the disadvantages. The important properties include include robustness to damage. For example, in the ant foraging example, if I walk along this path and accidentally or on purpose, if I'm a little toddler, squash an ant or two, that's not going to stop the ants foraging for food. They're going to be able to recover from that sort of damage. They're robust to damage to individuals. And that's because there is no one central ant who's in charge. Complex systems are also flexible to a problem change. If we move where the food source is in this example, the ants are going to be able to find that and reform their trail. They're also scalable. If we add more ants into the system or more food sources, they can handle a change in scale of the problem. That's much harder in engineered systems like highways. Can you imagine trying to design a highway on that scale? But it's important that we understand the principles so that we are able to do things like this. So there's some examples of what we mean by complex systems. Let's have a look at pulling out some of the similarities across these examples into a definition of what we mean. Here we're now looking at one of these emergent structures of fish as a great example of complex systems. And here let's start with a simple definition. Complex systems is the study of collective behavior, self-organization, and emergence. Here what we see is patterns that only occur at the collective scale. We don't get to see the fish behaving like this if there are only individuals. This is a collective behavior. It's also what we call self-organized. As I've said a few times tonight about our complex systems, there's no one individual that's in charge. The organization is collective. Each individual is interacting with its neighbors in order to achieve this organization. And what we get out of that is the emergence of a behavior like a tornado that we see here that we can't predict just by looking at individuals alone. Moving on to some deeper definitions of what complex systems are. Two of my favorites are here from authors Melanie Mitchell and Hiroki Siyama. Melanie Mitchell says a complex system is a system in which large networks of components with no central control and simple rules of operation give rise to complex collective behavior, sophisticated information processing, and adaptation via learning or evolution. Similarly, Hiroki Siyama says complex systems are networks made of a number of components that interact with each other, typically in a nonlinear fashion. Complex systems may arise and evolve through self-organization, such that they are neither completely regular nor completely random, permitting the development of emergent behavior at macroscopic scales. Those definitions are similar but subtly different. What I want to do is pick out some of the similarities between these that are some of the very important features of what complex systems are. Both of these authors identify that when we're talking about complex systems, we're talking about large systems of many, many individual components where there's no central control. We can see that in all of the systems we've looked at here. They're all large systems of many, many components. What's important in those systems, since there's no central control, is the interaction between those components through some kind of network structure. Those interactions are what leads to the behavior, the emergent behavior or the collective behavior at the systems level. We get interesting emergent behaviors at the systems level that we can't predict just by looking at the individuals, because these systems typically involve feedback between the components. So in the ant foraging example, what we see is when an ant finds some food, it lays down some pheromone, and that influences other ants to come along and come along and pick up the food as well and follow it back to the nest. That pheromone gradually forms a trail that the ants can sense to lead them to and from the food. That's called a positive feedback effect. One ant is leading the other to do the same behavior, which leads more and more ants to do the same again. Feedback is really important in complex systems. So too is nonlinearity. What happens is if we add more and more food sources, we don't just see the same kinds of behavior becoming more and more of the same behavior. We see different behavior. When we change the inputs to complex systems, more is different. More is not just more is different. They're nonlinear effects, and they're really important because that's another reason why we can't just predict what we're going to get at the systems level just by looking at individuals. We also see a mix of regularity and randomness in these systems. Usually when we're talking about engineered systems, like the internet or traffic, usually we're trying to get something very regular that's very predictable. For example, very regular traffic flows, trying to avoid anything unpredictable coming up. When the systems are complex, though, that's very difficult. Complex systems don't just behave regularly. We see this again in the ant foraging example. The ants exhibit an interesting mix of regular and chaotic behavior. They use regular behavior to exploit the environment once they've worked it out. Once they've got the food sources identified and are bringing them back to the nest, we're seeing these very regular foraging trails. But even while the trails are there, and in particular beforehand, the ants are exploring the environment. You'll see them walking around a little bit randomly, trying to find potential food sources or better food sources than we have here. That interplay between regularity and randomness is really important for complex systems being so flexible. We also see very sophisticated information processing in all of these complex systems. We talked about the Trafalgar effect in the fish before as a way that fish are very efficiently able to transfer important information about predators, for example. It's a truism to talk about the sophisticated information processing in the brain, obviously, as well. In all of these examples here, the solutions that the systems have come up with to the problems that they face have arisen through some evolutionary process or adaptation. It's very difficult to hand design engineered solutions to complex systems. We typically need more advanced tools to achieve this, and we can learn from what nature does with evolutionary behavior, for example, to design better engineered systems. So that's what complex systems. That's what complex systems are. These are the kinds of things that we're dealing with. In the next few slides, I'm going to talk about some of the interesting features of complex systems, one by one. The first feature to mention here is emergence. We've already gone through this one a little bit when we talked about the emergent behavior in the schooling of fish, that we can get very interesting macroscopic patterns, like all the fish heading in one direction, like the terns, like the tornadoes. Emergent behavior is something that we just can't predict if we look at the individuals in the system alone. Importantly, when it comes to studying complex systems, the complex systems can be modeled and they can be simulated. And this is really important, particularly when we're talking about our Master of Complex Systems degree and our Introduction to Complex Systems unit of study. This is our primary focus. How can we model and simulate complex systems? To pause here for a moment, we need to think about what modeling means. Modeling means to form a representation of a system. And there's a lot of different types of modeling, a lot of different ways we can do that. We can form mathematical models of systems. For example, if we wanted to think about modeling epidemic disease spreading like COVID, we can form a mathematical model of, if we think about our population as having people who have the disease or who are immune or who are susceptible, we could form differential equations to relate those three together in our system. We could form computational models where we actually model every individual in the population moving around and catching the train and going to work and having a whole lot of potential events where they could be infected from an infected person, and form a much more detailed computational model. There are different pros and cons of the different types of models, and these are things that we consider in our Introduction to Complex Systems course. One that I want to show you briefly here is a way of modeling the foraging of ants that we see over on the right panel here. This is in a system, a programming environment called NetLogo. I'll bring this up briefly to show you. Where are we? Okay, so NetLogo is a programming environment that's designed for a type of modeling called agent-based modeling. This is a type of modeling where we create a computational entity or an agent to represent each individual in the system. Here what we have is a representation of each individual ant. The graphics are obviously very simple. The point isn't to have beautiful graphics like a computer game. The point is to understand what's happening with the ants. We have a nest in the middle and 3 modeled food sources around the edge. And what we can do in that logo is watch what happens when we release the ants into the environment and they start to interact. And what we see is in this model, each ant, when it finds the food source, it picks up some food and takes it back to the nest, and it drops some chemical, these pheromones, on the ground behind it. Those pheromones attract other ants to that trail, and that helps them to find the food source and to exploit it. And what we can see here is as more and more ants hit that trail, we will see them forming a trail that lasts to bring all of the food source back to the nest until the food source is exhausted. This model is very simple. The ants are very, very simple in this model, and yet we see the same kinds of behavior that we get from real world ants. That tells us a lot. It tells us that the set of rules that we've implemented for the ants here are sufficient to recreate the behavior. We don't need to add anything more complex. We could fit our parameters a bit more closely to generate behavior that's more close to one specific species of ants rather than another. We could do that. We need to think about what we want to get out of our model and how accurate we want it to be. Here, in terms of explaining how ants form foraging trails, we can keep it simple, and the simpler the better, because then we know we've put in the minimal assumptions possible to explain the type of behavior that we see. Okay, let's go back to the presentation here. Okay. So another important feature of complex systems is that we have network effects. The components in our system are connected to one another in different ways. For example, in a social network, we have links that can mean different things. It can mean we might be looking at who I interact with on a daily basis. We might be looking at Facebook or Twitter and looking at who the connections are there. Or in a disease modeling situation, we might be looking at modeling who I interact with that I could catch the disease from. That last example is particularly important. Some of my colleagues at our Complex Systems Research Group at the University of Sydney have been doing agent-based modelling work to look at understanding how COVID-19 spreads and to understand the efficacy that interventions like lockdowns can have. And they've had quite a lot of media attention this year due to the interesting work they've been doing there. Those interventions can include looking at interrupting the network, interrupting the flight network across the world, for example, and that's an intervention that has been particularly successful for Australia, as I say. There are other kinds of networks, not just social networks, that we could look at as well. We could look at power grid networks, are another interesting example. What we're looking at here is a power grid network in the west coast of the United States, where a failure has occurred on one node in the network, and that failure is gradually spreading. The little red dots are telling us which nodes are falling over as each step in time progresses. What's happened is we had an initial failure on the network that led to overloads in surrounding nodes, which led those to fall over as well, which led to other overloads. And gradually the whole system starts to go down. And the red points are where nodes are falling over. The blue is the parts of the network that have already been taken out. So we need to understand network structure and its effect on the dynamics of complex systems in order to manage failures like this. What's interesting in systems like power grids is we see the same kind of order-chaos interplay that we talked about with the ant foraging before. Here, what I mean by an order-chaos interplay is that in some regimes, we have very stable dynamics on our power grids. A failure in one section of the network won't typically spread very far. But under different sets of parameters, we can get regimes where a failure in any one area of the network can spread very quickly and overwhelm the entire network. So we need to tune our system so that it's not in that bad regime. Another feature of complex systems that is important for us is that they are difficult to predict. And this is because we have these emergent effects that we see, effects that occur at a systems level that we can't understand just by looking at individuals in the system. Traffic is a great example for this. When you're driving your car along the freeway, you're typically just looking at the few cars that are in front or around you, and you're reacting to them. Obviously, you want to get to your destination as soon as possible, so you're hitting the pedal to the metal down the freeway and burning along. But if the person in front of you starts to brake, obviously you need to react to that. There are things that happen on freeways that we can't understand just by thinking about individual cars. Have you ever been in what's known as a shockwave, where you're driving along the freeway and all of a sudden all the cars in front are starting to bank up and you have to come to a halt? And you wait there for a couple of minutes and then the cars start to take off again, and you take off too, and you're looking around and there's no car accident that you're going past. There's no spill on the side of the road, nothing that would indicate that we should have had a big traffic jam like that. And you go on your merry way and wonder what happened. That's called a shockwave. Those are emergent effects that we can have in traffic due to interactions in a complex system like this that we can't understand just by looking at individuals. What we can do is to simulate them and try and understand them a little better by simulating them. And I'll pull out another prepared piece of code here from NetLogo, where we can fairly quickly simulate just a single lane of traffic. It's kind of a circular lane, so the cars come off the right here and come back on at the left. And fairly quickly we can see when we start the simulation up is that we get these shockwaves occurring very quickly. If we focus on the red car, we can see for a while it's going along really nicely, and then bang, it has to stop, and after a while it starts again. What we can do is we can play with the different parameters for our model to try and understand why these behaviors occur and how to avoid them. The short answer to why they occur is basically that all of us as humans driving a car have finite reaction times. So if the person in front of us brakes, it takes us maybe a few hundred milliseconds before we realize they've started braking, before we have to hit the brakes ourselves. By the time we hit the brakes, we have to brake a little bit harder than they did, which means the person behind us has to slow down harder again, because we had to slow down harder to avoid the person in front. They have to slow down harder again to avoid us. And of course, their own reaction time makes that worse. You can see how that effect banks up and banks up and banks up before pretty quickly all the traffic starts to stop, maybe 10 or 15 cars behind me, and they weren't even involved in the initial braking themselves. And they're the ones that wander off when the traffic restarts, wondering what happened. We can play with parameters in models like this to try and understand why that happens and how to avoid it. What we can do here is reduce the number of cars on the road. If we bring this down to around 15 and let it run again, pretty quickly those shockwaves start to flatten out. We can still see a little bit here, but the cars are moving, and we're actually getting a much larger average and maximum speed than we had in the earlier regime when we had more cars on the road. So it turns out that by reducing the density of cars, and we can also achieve the same thing by lowering the maximum speed limit, we can get more cars down the road per unit time. We can get a better flow with either less cars or a lower maximum speed. This is coming back to the nonlinear effects that I was talking about before. More in terms of speed or cars does not mean more throughput. More is different in complex systems. Coming back to the slides, this is what we were talking about complex systems being difficult to predict, particularly because they involve nonlinear effects. And this is precisely why you see those variable speed limit signs on the freeway. What happens is once the density of cars becomes too high, we have a very high propensity for these shockwaves to form. So we can actually get better flow on the freeway by counterintuitively dropping the maximum speed. So that's a really interesting complex systems effect. Okay. So hopefully it's started to become clear to you by now why we're interested in complex systems. Complex systems are all around us, both in biology, in terms of understanding how diseases spread, to managing ecosystems, to trying to understand complex effects in the human brain, right through to engineered systems like traffic, like the internet, and so on. In particular, understanding complex systems or complexity is becoming more and more relevant as our systems increase in scale and their level of interconnectivity. We can see that coming back to the example of COVID-19. Because of the level of interconnectivity in our global world today, these diseases can spread much more quickly across the planet than they ever could before. So it's much more important for us to understand the effect of interconnectivity in complex systems than it ever was. Furthermore, complex systems aims to address big picture questions in all of these fields. We want to understand how to model collective behavior in these large systems. We want to understand how to analyze how the self-organization in these systems leads to the whole of the system being greater or different to the sum of the parts, like in the traffic example that we looked at. We want to understand how we can predict the future behavior of systems when there are so many interdependencies that take place there, using approaches such as modeling and simulation. We want to understand how to identify signatures of what we call critical behavior. Coming back to the power grid example, how to understand when our power grid is in a regime where any one failure will take down the whole entire network. How can we identify signatures that we're in those sorts of regimes and that they're impending crises? And in particular, what can we learn from nature for designing human-engineered systems like traffic and like the internet? In the last couple of minutes then, now that we've talked a lot about what complex systems are and why we might be interested in them, we'll have a little short look at what we talk about in our Introduction to Complex Systems subject and in the wider degree. Introduction to Complex Systems is our foundational subject.
for a virtual round of applause for Associate Professor Joseph Lissier, who gave us a fantastic masterclass, and I hope we all learned a lot today. No?
Thank you, and thank you guys for the opportunity for you've given me to speak, and thanks to the audience as well. I hope you enjoyed it, whether it's live or on a recording later on.
Thank you very much.